Earth orbits the Sun at 67,000 miles per hour. The Sun orbits the center of the Milky Way at 514,000 miles per hour. But the Milky Way itself is moving, racing through space at over 1.3 million miles per hour, pulled by an invisible force. What could pull an entire galaxy? Not just our galaxy, but thousands of galaxies, a region of space containing as much mass as tens of thousands of Milky Ways, all streaming in the same direction like rivers flowing toward an ocean. This cosmic destination has a name: the Great Attractor. For most of human history, we thought Earth was stationary, the unmoving center of creation. The stars wheeled overhead, the planets wandered, but our world remained fixed, the still point around which everything revolved. This geocentric worldview persisted for millennia, reinforced by philosophy, religion, and the simple evidence of our senses. When we look outside, we don't feel the ground moving beneath our feet. Then came Copernicus, who in 1543 published his revolutionary idea that Earth orbits the Sunday. This heliocentric model placed our planet in motion for the first time, spinning on its axis once per day and circling the Sun once per year. The idea was controversial, even dangerous. It displaced humanity from the cosmic center and set us adrift in space. Galileo's telescopic observations supported Copernicus. He saw Jupiter's moons orbiting Jupiter, proving that not everything circles Earth. He observed Venus's phases, consistent only with a heliocentric model. Slowly, the scientific community accepted that Earth moves. But how fast? Johannes Kepler worked out the mathematics of planetary orbits, and later astronomers calculated Earth's velocity, approximately 30 kilometers per second, or about 67,000 miles per hour. We orbit the Sun at tremendous speed, yet feel nothing. The smoothness of our motion creates no sensation, only the passage of seasons marks our journey around our star. Yet, even this was not the full picture. In the 18th and 19th centuries, astronomers began to suspect that the Sun itself moves through space. By carefully measuring the positions of nearby stars over years and decades, they detected proper motion, slight drifts in stellar positions against the background of more distant stars. William Herschel, in the 1780s, analyzed the proper motions of stars and concluded that the Sun moves toward a point in the constellation Hercules. Stars in that direction appeared to spread apart, while stars in the opposite direction converged, like trees along a road as you drive forward. The Sun had a destination; it was traveling through the galaxy, but the galaxy itself was barely understood. Throughout the 19th century, astronomers debated the nature of the fuzzy nebulae visible in their telescopes. Were they clouds of gas within our stellar system, or distant collections of stars, island universes in their own right? The Great Debate of 1920 brought this question to a head. Harlow Shapley argued that the Milky Way was essentially the entire universe, a vast system of stars with the Sun somewhere off-center. Heber Curtis argued that spiral nebulae were separate galaxies, implying a universe far larger than the Milky Way alone. Edwin Hubble settled the debate in 1923 to 1924, when he identified Cepheid variable stars in the Andromeda Nebula. These stars have a known relationship between their brightness and their pulsation period, allowing astronomers to calculate distance. Hubble's measurements showed Andromeda was nearly 1,000,000 light-years away, far beyond the Milky Way's boundaries. The spiral nebulae were indeed separate galaxies, and the universe suddenly grew enormously larger. Hubble went further. By measuring the spectra of galaxies, he discovered that most showed red-shifted light wavelengths stretched to longer, redder values. Moreover, the amount of redshift increased with distance. Farther galaxies receded faster. In 1929, Hubble announced what became known as Hubble's law. The velocity of a galaxy's recession is proportional to its distance from us. This relationship, velocity equals the Hubble constant times distance, implied something profound. The universe is expanding. Space itself stretches, carrying galaxies apart like raisins in rising bread dough. The expansion isn't galaxies moving through space, but space itself growing. This discovery established the framework for understanding cosmic motion. Galaxies move through expanding space, their motion a combination of the overall Hubble flow, carrying them apart, and local gravitational influences, pulling them toward nearby masses. The Sun's motion within the Milky Way was eventually quantified at about 220 kilometers per second, 514,000 miles per hour, as it orbits the galactic center every 230 million years or so. One galactic year ago, dinosaurs hadn't yet appeared on Earth. The Milky Way has rotated perhaps 50 times since the Sun formed. But what about the Milky Way itself? Did our entire galaxy have a motion through space, beyond the universe's expansion? Initially, astronomers assumed the Milky Way's motion was essentially random, a small local velocity superimposed on the Hubble flow, reflecting gravitational tugs from nearby galaxies. No one expected coherent, large-scale motion. This assumption began to crumble in the 1970s when astronomers developed new techniques for measuring galaxy distances and velocities with high precision. The key innovation was finding standard candles and standard rulers objects or relationships that allowed distance determination independent of redshift. If you know an object's intrinsic brightness, you can determine its distance by measuring how bright it appears. A 100-watt light bulb appears dim if far away, bright if nearby. Astronomical standard candles work the same way. Type Ia supernovae, for example, have roughly the same luminosity, making them excellent distance indicators for faraway galaxies. For nearer galaxies, astronomers used relationships within the galaxies themselves. The Tully-Fisher relation, discovered by R. Brent Tully and J. Richard Fisher in 1977, relates a spiral galaxy's luminosity to its rotation speed. Faster rotating spirals are more luminous. By measuring rotation speed from spectral line widths, astronomers could estimate luminosity, compare it to observed brightness, and derive distance. Similarly, the Faber-Jackson relation, later refined into the fundamental plane, connected elliptical galaxies' luminosity to their velocity dispersion, how fast stars move within the galaxy. These relationships provided distance estimates for thousands of galaxies. With distances in hand, astronomers could calculate what velocity each galaxy should have from the Hubble flow alone, v equals h0 times d, where h0 is the Hubble constant and d is distance. Comparing this predicted velocity to the observed velocity from redshift revealed peculiar velocities deviations from the smooth Hubble flow. Peculiar velocities should arise from gravitational interactions. A galaxy near a massive cluster would be pulled toward it, gaining an extra velocity component beyond the Hubble flow. Astronomers expected these peculiar velocities to be small and randomly oriented, reflecting local gravitational tugs. What they found was shocking. In 1976, Vera Rubin and colleagues noticed that the rotation curves of galaxies, how orbital velocities vary, with distance from galactic centers remained flat, far beyond where visible matter ended. This implied enormous amounts of unseen dark matter in galaxy halos. Though not directly related to the Great Attractor, this discovery would later prove crucial for understanding cosmic structure. In the late 1970s and early 1980s, surveys of galaxy redshifts revealed coherent patterns. Galaxies weren't moving randomly. Across vast regions, they showed systematic velocity excesses or deficits compared to the Hubble flow, as if entire volumes of space were streaming in particular directions. The breakthrough came in 1986 when a team of 7 astronomers, Sandra Faber, David Burstein, Roger Davies, Alan Dressler, Robert Lindenbell, Roberto Terlevich, and Gary Wegner, published a landmark paper. Known as the Seven Samurai, they had measured distances and velocities for 400 elliptical galaxies using the Faber-Jackson relation and its refined version. Their data revealed something astonishing. The local group, our cosmic neighborhood, including the Milky Way, Andromeda, and about 50 smaller galaxies, was moving at approximately 600 kilometers per second, 34 million miles per hour, toward a region in the southern sky near the constellations Centaurus and Hydra. This wasn't just our local motion. The Virgo cluster, a major galaxy cluster about 54 million light-years away, was also moving in roughly the same direction. So were more distant galaxies and clusters. A vast river of galaxies, spanning hundreds of millions of light-years, was flowing coherently toward a common destination. The Seven Samurai called this destination the Great Attractor. The name captured the imagination. Here was a gravitational anomaly so powerful it pulled thousands of galaxies across hundreds of millions of light-years. What could be so massive? Where was it, and why couldn't we see it? Initial estimates placed the Great Attractor approximately 150 to 250 million light-years away, with a mass of roughly 5 times 10^16 solar masses, equivalent to 50,000 Milky Way galaxies. Such a concentration would create an enormous gravitational well, bending the paths of galaxies across a substantial fraction of the observable universe. But when astronomers pointed their telescopes toward the Great Attractor's predicted location, they saw almost nothing. The region lay behind the Milky Way's disk, obscured by dust and stars. It was hidden in what astronomers call the zone of avoidance, a cosmic blind spot where our own galaxy blocks the view. The Great Attractor was real. The galactic velocities proved something massive existed, but it remained invisible, a gravitational phantom shaping our motion through the cosmos. The Milky Way stretches across Earth's night sky like a luminous river, a band of light composed of billions of distant stars in our galaxy's disk. For millennia, people gazed at this celestial wonder, spinning myths and legends about its origin. The ancient Greeks called it the Milky Circle, imagining it as milk spilled by Hera. Other cultures saw it as a road, a river, or the backbone of the night. Modern astronomy reveals the Milky Way as our edge-on view of a spiral galaxy. We're embedded within the disk, looking outward through 100,000 light-years of stars, gas, and dust. The concentration of stars creates the glowing band. The patchy darkness comes from intervening dust clouds. This dust, microscopic grains of carbon, silicates, and ices, pervades the interstellar medium. Though each grain is tiny, collectively they absorb and scatter visible light. A photon of starlight, traveling toward Earth from a distant galaxy, might be absorbed by a dust grain, its energy converted to heat. or it might scatter, deflected from its path. Either way, dust dims the light from objects behind it. Near the galactic plane, the imaginary line marking the Milky Way's central disk dust is most concentrated. Here, extinction, the dimming of light, can be severe. A galaxy that would be easily visible if located elsewhere in the sky becomes invisible when positioned behind the galactic plane. This creates the zone of avoidance, roughly 20% of the sky where external galaxies are extremely difficult or impossible to observe at optical wavelengths. The zone isn't sharply defined. Extinction varies depending on the exact line of sight and how much dust lies along it, but generally, within 10 to 15 degrees of the galactic plane, extragalactic observations become problematic. The zone of avoidance isn't empty. Plenty of galaxies exist in those directions. We just can't see them. It's like trying to observe a parade through a foggy window. You know the parade is there, you can hear it, but the fog blocks your view. Astronomers have mapped the zone of avoidance's variable extinction using star counts and colors. More dust means fewer visible stars. Dust reddens starlight by scattering blue wavelengths more than red. These maps reveal a complex, patchy structure. Some lines of sight are more transparent than others, creating windows through the fog. The Great Attractor lies at galactic coordinates near L, is approximately equal to 320 degrees. B is approximately equal to -7 degrees. That's within the zone of avoidance, though not at the very worst position. Still, extinction in visible light is substantial factors of 10 to 100 or more in some areas. Galaxies that would shine at magnitude 12 elsewhere appear as magnitude 17 or fainter here, if visible at all. This posed an enormous challenge. The Great Attractor's gravitational influence was undeniable, the velocity data was clear, but directly studying its structure required seeing through the Milky Way's obscuring veil. Astronomers turned to longer wavelengths. The key insight is that dust affects different wavelengths differently. Visible light, with wavelengths around 400 to 700 nanometers, is strongly absorbed and scattered. Infrared light, with wavelengths from about 1 to 100 micrometers, penetrates dust much more easily. Radio waves, with wavelengths from millimeters to meters, pass through dust almost unimpeded. The physics is straightforward. Dust grains are most effective at blocking light, with wavelengths comparable to their size. Optical wavelengths are similar in size to typical interstellar dust grains, so interaction is strong. Infrared wavelengths are larger than dust grains, so they diffract around them with less absorption. Radio wavelengths are enormously larger, making dust effectively invisible at those frequencies. Infrared astronomy offered the first window into the zone of avoidance. Ground-based infrared observations began in the 1960s and 1970s, though atmospheric absorption limited their effectiveness. Water vapor in Earth's atmosphere absorbs many infrared wavelengths, forcing observations from high, dry sites or from space. The Infrared Astronomical Satellite, IRAS, launched in 1983, surveyed the entire sky at infrared wavelengths for the first time. IRAS detected thousands of previously unknown galaxies, including many in the zone of avoidance. Its data hinted at overdensities regions with more galaxies than average in the direction of the Great Attractor. The 2-micron all-sky survey, 2MASS, conducted from 1997 to 2001, mapped the sky in near-infrared bands at 1.25, 1.65, and 2.17 micrometers. At these wavelengths, dust extinction is reduced by factors of 10 compared to visible light. 2MASS detected millions of galaxies, including many hidden in the zone of avoidance, and identified several significant galaxy clusters and overdensities behind the Milky Way. The Spitzer Space Telescope, launched in 2003, observed at mid-infrared wavelengths from space, free from atmospheric interference. Spitzer could see through even thicker dust, revealing deeply embedded objects. Though not primarily a survey telescope, it contributed observations of specific regions in the zone of avoidance. Radio astronomy provided another crucial window. Neutral hydrogen atoms emit radiation at a wavelength of 21 centimeters, a frequency of 1,420 megahertz, when the electron's spin flips relative to the protons. This 21 cm line is extremely useful because hydrogen is abundant in galaxies, and the radiation passes through dust with minimal absorption. By mapping 21 cm emission, radio telescopes can detect galaxies by their hydrogen content, even when optical and near-infrared observations fail. The Parkes Radio Telescope in Australia conducted extensive surveys of the zone of avoidance's southern sections, discovering hundreds of previously unknown galaxies. X-ray observations offered yet another window. Hot gas in galaxy clusters emits X-rays through thermal Bremsstrahlung and line emission. X-rays penetrate the Milky Way's dust reasonably well, though our galaxy's gas causes some absorption at soft X-ray energies. Satellites like ROSAT, Chandra, and XMM Newton detected X-ray emission from hot gas in clusters behind the galactic plane, revealing massive structures invisible at optical wavelengths. These multi-wavelength observations gradually revealed the Great Attractor region's structure. What emerged was not a single, monolithic object, but a complex web of galaxies, groups, and clusters, a convergence of cosmic structure where multiple components contribute to the total gravitational pull. The Norma Cluster Abell, 3627, stands as one of the Great Attractor's major components. Located about 220 million light-years away, at galactic coordinates L equals 325 degrees, B equals -7 degrees, the Norma cluster sits almost at the predicted Great Attractor center. It's a rich cluster containing hundreds of galaxies, with a total mass estimated at 10-15 solar masses, about 1,000 times the Milky Way's mass. The Norma cluster was difficult to recognize earlier because of its location in the zone of avoidance. Optical surveys had catalogued few galaxies there. Infrared and X-ray observations revealed its true nature. A massive, dense cluster that contributes significantly to the Great Attractor's gravitational pull. Near the Norma cluster lie other significant structures. The Centaurus cluster, about 150 million light-years away, contains several hundred galaxies and was one of the earliest recognized contributors to the local gravitational flow. The Hydra cluster, roughly 200 million light-years distant, adds to the mix. The Pavo-Indus supercluster, the Telescopium Norma supercluster, and various galaxy groups fill the region. Together, these structures form the Great Attractor complex, a convergence of multiple mass concentrations that collectively create the gravitational anomaly pulling galaxies toward it. It's not a single object, but a region, a nexus where the cosmic web's filaments intersect, creating an overdensity spanning tens of millions of light-years. But as observations improved, a puzzle emerged. Even accounting for all the visible galaxies, hot gas, and estimated dark matter in the Great Attractor region, the total mass didn't seem sufficient to explain the observed velocities. Galaxies were moving too fast toward the Great Attractor. Something else must be contributing. Additionally, when astronomers carefully analyzed the velocity field, they found residual motion even after subtracting the Great Attractor's influence. Our region of space wasn't just falling toward the Great Attractor, we were moving towards something beyond it. This led to the discovery of the Shapley supercluster, an even more massive concentration lying behind the Great Attractor. Beyond the Great Attractor, approximately 650 million light-years away in the direction of the constellation Centaurus, lies the most massive concentration of galaxies in the nearby universe, the Shapley supercluster. The Shapley supercluster takes its name from Harlow Shapley, the astronomer who first noted an unusual concentration of galaxies in this region during the 1930s. Shapley was conducting photographic surveys of the southern sky, cataloguing galaxies and their distributions. He noticed that one area in Centaurus contained a remarkable overdensity, far more galaxies per square degree than typical sky regions. At the time, the significance wasn't fully appreciated. Shapley documented the concentration but couldn't determine its distance or full extent. It would take decades of further observation before astronomers recognized the Shapley concentration, as it's often called, as a supercluster, a collection of multiple galaxy clusters gravitationally interacting and forming one of the universe's largest structures. Modern observations reveal the Shapley supercluster as a magnificent cosmic structure. It contains at least 25 individual galaxy clusters, plus numerous smaller groups, all concentrated in a relatively compact volume, about 200 million light-years across. The total galaxy count exceeds 8,000 large galaxies, with countless dwarf galaxies adding to the population. The Shapley supercluster's mass is staggering. Estimates range from 10, 16 to 10, 17 solar masses, 10,000 to 100,000 times the Milky Way's mass. This makes it one of the most massive structures within the nearby billion light-years, exceeded only by a handful of other superclusters. Several prominent galaxy clusters anchor the Shapley supercluster. Abell 3558, located near the supercluster's center, is one of the richest clusters known, containing over 1,000 galaxies within a relatively small volume. X-ray observations show it surrounded by hot gas at temperatures exceeding 100 million degrees, a sure sign of an enormous gravitational well holding the gas in place. Other major clusters include Abell 3556, Abell 3560, Abell 3562, and the Abell S 736 complex. These clusters aren't isolated islands but are connected by bridges of galaxies, forming a continuous web of structure. Some clusters appear to be merging, their galaxies and gas halos colliding in slow-motion cosmic encounters lasting hundreds of millions of years. The Shapley supercluster's gravitational influence extends far beyond its visible boundaries. Just as the Great Attractor pulls the Milky Way, the Shapley supercluster pulls the Great Attractor and us along with it. Our motion toward the Great Attractor is itself being redirected toward Shapley, creating a hierarchical cascade of gravitational attraction. Velocity studies confirm this picture. When astronomers analyze the peculiar velocities of galaxies in the Great Attractor region, They find that these galaxies are not stationary relative to the cosmic microwave background, CMB. They're moving toward Shapley at several hundred kilometers per second. This motion adds to ours, since we're falling toward the Great Attractor, which is falling toward Shapley. The total picture becomes clearer. We're part of a vast gravitational river system. Galaxies flow toward local concentrations, like the Virgo cluster, which flow toward larger concentrations, like the Great Attractor, which flow toward even larger concentrations, like the Shapley supercluster. Each level of the hierarchy contributes to the overall velocity. Our measured peculiar velocity, approximately 627 kilometers per second toward a point in Centaurus, reflects this layered structure. Different studies partition the motion differently, but roughly, the local group moves toward the Virgo cluster at about 200 to 300 kilometers per second. The Virgo region moves toward the Great Attractor at about 300 to 400 kilometers per second. The Great Attractor region moves toward the Shapley supercluster at about 200 to 300 kilometers per second. These velocities don't simply add, since they point in somewhat different directions, but their vector sum produces our net motion of about 627 kilometers per second toward the overall center of mass of all these structures. The Shapley supercluster's discovery and characterization resolved much of the missing pull problem that had puzzled astronomers. The Great Attractor alone couldn't account for observed velocities. Shapley, lying beyond and pulling both us and the Great Attractor, completed the picture. But is there something beyond Shapley, pulling it in turn? Possibly. Some studies suggest excess velocity even after accounting for Shapley's influence. Potential contributors include the Vela supercluster, discovered in 2017, lying partly in the zone of avoidance at about 800 million light-years, and other distant structures. The cosmic flow toward Shapley eventually terminates, however. The universe's expansion carries distant regions away faster than gravity can pull them toward us. At some distance, recession wins, and objects no longer contribute to our peculiar velocity. The sphere within which gravitational influence dominates over expansion defines our effective horizon for peculiar motions roughly 1 billion light-years in radius. Within this horizon, we're part of a grand flow, a cosmic river carrying us toward the greatest mass concentrations. Beyond it, the universe expands too fast for gravity to reach us, and we're carried apart regardless of distant masses. In 2014, R. Brent Tully, Hélène Courtois, Yehuda Hoffman, Daniel Pomered, and their colleagues published a paper that transformed our understanding of cosmic structure. Using a novel approach based on galaxy velocities rather than just positions, they mapped the large-scale flow of matter around us and discovered we belong to an immense supercluster they named Laniakea. The name comes from Hawaiian, Lani meaning heaven and Akea meaning immense or spacious. Laniakea, the immense heaven, spans approximately 520 million light-years across and contains roughly 100,000 galaxies similar in size to the Milky Way, plus countless smaller ones. Traditional supercluster definitions relied on galaxy density regions with more galaxies than average were called superclusters, but this approach had limitations. Where does one supercluster end and another begin? Density gradients are often gradual, making boundaries arbitrary. Tully's team used a different approach. They mapped the velocity field. By measuring peculiar velocities for thousands of galaxies, They could trace the flow of matter which way galaxies were moving relative to the CMB rest frame. The key insight was that galaxies flow toward mass concentrations. Think of water on a landscape. It flows downhill toward basins, and the boundaries between drainage basins, watersheds, define distinct regions. A drop of rain on one side of a ridge flows to one lake. A drop on the other side flows to another. Similarly, galaxies on one side of a velocity watershed flow toward one attractor. Galaxies on the other side flow toward a different attractor. By identifying these watersheds in the cosmic velocity field, Tully's team could delineate superclusters as distinct basins of gravitational attraction. Laniakea is our basin. The Milky Way, the Local Group, the Virgo Cluster, the Great Attractor, and the Shapley Supercluster all belong to it. They're all part of the same flow, directed toward a common center of mass. Laniakea's boundaries, the watersheds separating it from neighboring superclusters, were mapped using the velocity data. On one side lies the Perseus-Pisces supercluster, where galaxies flow toward a different attractor. On another side is the Coma supercluster. The boundaries aren't walls but dividing lines in the velocity field. Galaxies near them move slowly, nearly balanced between competing attractions. The Milky Way lies near Laniakea's edge, in a region called the Local Sheet, a relatively flat distribution of galaxies that includes our local group. We're not near Laniakea's center. Instead, we're in the cosmic suburbs, flowing inward toward the denser core. Near Laniakea's center lies the Great Attractor region, the gravitational nexus toward which galaxies throughout the supercluster flow. But the center isn't a single point. It's an extended region where multiple mass concentrations, including the Norma cluster and other structures, create the deepest gravitational potential. Laniakea's discovery redefined our cosmic address. For decades, astronomers had said we live in the Virgo supercluster, a structure about 110 million light-years across, centered on the Virgo cluster. But the Laniakea analysis showed the Virgo supercluster is just one component of a larger whole. It's not a separate entity, but a lobe or appendage of Laniakea. Our updated cosmic address reads: Earth, Solar System, Orion Arm, Milky Way Galaxy, Local Group, Local Sheet, Laniakea Supercluster, within which lies the former Virgo supercluster. This reframing matters because it reflects gravitational reality. The Milky Way isn't just a neighbor of the Virgo cluster. It's part of the same dynamical system, flowing through the same basin toward the same center. Laniakea is our true cosmic home. Laniakea's structure is filamentary and web-like, reflecting the cosmic web's architecture. Dense nodes, galaxy clusters, connect via filaments, linear galaxy concentrations, surrounding vast voids, regions with few galaxies. The Great Attractor lies at a major node where several filaments converge. One notable filament extends from the Local Group toward the Virgo cluster. The galaxies along this filament constitute part of what was called the Virgo supercluster. Another filament connects through the Centaurus cluster toward the Great Attractor. The Shapley supercluster, though part of Laniakea, lies toward Laniakea's edge, where flows begin transitioning to other basins. The dynamics within Laniakea are complex. Not every galaxy falls directly toward the center. Some orbit within clusters, held by local gravitational wells. Some participate in larger orbits around the supercluster's center of mass. Others are falling inward but will overshoot and oscillate back. Over cosmic time, These motions gradually dissipate, and galaxies settle into the supercluster's deepest potential wells. Importantly, Laniakea is not gravitationally bound. The velocities of galaxies flowing toward its center are insufficient to overcome cosmic expansion for galaxies near the edges. Eventually, dark energies accelerating expansion will pull Laniakea apart, isolating its constituent clusters into separate islands receding from each other. This distinguishes Laniakea from smaller structures like galaxy clusters, which are gravitationally bound. Their members will remain together forever, or until they merge into a single object. Superclusters like Laniakea represent the largest coherent structures, but they're transient on cosmic timescales, destined for dissolution as expansion accelerates. Still, for now and for billions of years to come, Laniakea defines our cosmic neighborhood, a basin of attraction spanning 500 million light-years, within which tens of thousands of galaxies flow toward a common destiny. To understand why galaxies flow toward the Great Attractor, we must explore gravity on cosmic scales and how structure emerges in an expanding universe. Gravity, as Isaac Newton described it, is an attractive force between masses. Every particle of matter attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. This simple law explains planetary orbits, falling apples, and the motions of stars within galaxies. Albert Einstein deepened our understanding with general relativity, which describes gravity not as a force but as the curvature of space-time caused by mass and energy. Objects move along the straightest possible paths through curved space-time, and those paths curve toward massive objects. The effect is the same masses attract, but the mechanism is geometric rather than force-based. On cosmic scales, gravity competes with the universe's expansion. Space itself stretches, carrying galaxies apart. Without gravity, expansion would simply dilute matter, spreading galaxies ever farther apart at an ever-increasing rate. But gravity fights back. Regions slightly denser than average have stronger gravitational pull. They attract surrounding matter, growing denser still. This positive feedback gravitational instability is the engine of cosmic structure formation. The process began in the early universe. Shortly after the Big Bang, matter was distributed almost uniformly, imprinted during cosmic inflation, a period of extremely rapid expansion in the universe's first moments, served as seeds for all future structure. As the universe expanded and cooled, gravity amplified these seeds. Slightly overdense regions pulled matter from surrounding underdense regions. The rich got richer, the poor got poorer. Overdense regions grew denser, eventually collapsing to form galaxies, groups, and clusters. Underdense regions emptied out, becoming the vast cosmic voids we observe today. Dark matter played a crucial role. Comprising about 85% of the universe's matter, dark matter interacts gravitationally but doesn't emit, absorb, or scatter light. In the early universe, ordinary matter, protons, neutrons, electrons, was coupled to radiation, photons, which prevented it from clumping. Radiation pressure pushed outward, counteracting gravity's inward pull. Dark matter, unaffected by radiation, could collapse freely. It formed gravitational Wells halos, while ordinary matter remained smooth. Only after the universe cooled enough for ordinary matter to decouple from radiation, about 380,000 years after the Big Bang, could it fall into the dark matter halos. This is why dark matter dominates cosmic structure. It had a head start, collapsing earlier and creating the scaffolding upon which ordinary matter later accumulated. Galaxies formed at the centers of dark matter halos. Galaxy clusters formed where multiple halos merged into larger conglomerations. The Great Attractor is fundamentally a dark matter structure, a massive overdensity in the dark matter distribution, within which visible galaxies and hot gas reside. The visible components contribute only about 15% of the total mass. The remaining 85% is dark matter, invisible but gravitationally dominant. The flow of galaxies toward the Great Attractor follows from simple physics. Mass creates a gravitational potential, a field describing the energy required to move objects within it. Galaxies move from regions of higher potential energy toward regions of lower potential energy, just as balls roll downhill. The Great Attractor's enormous mass creates a deep potential well, a gravitational valley spanning hundreds of millions of light-years. Galaxies across this vast region feel the pull and flow toward the valley's bottom. But this flow competes with cosmic expansion. The Hubble flow carries galaxies apart at a rate proportional to their separation. More distant galaxies recede faster. For galaxies close to the Great Attractor, the gravitational pull exceeds the expansion rate, and they fall inward. For galaxies farther away, expansion dominates, and they're carried outward despite the gravitational attraction. The boundary between these regimes, where gravity and expansion balance, defines the extent of the Great Attractor's influence. Within roughly 300 to 400 million light-years, galaxies are in net infall toward the Great Attractor, though the exact boundary depends on direction and local density. Beyond this, expansion wins. The actual motion of galaxies is more complex than simple free fall. Galaxies have angular momentum. They're not falling straight toward the Great Attractor, but spiraling inward along curved paths. This angular momentum prevents direct collapse, just as Earth's orbital motion prevents it from falling into the Sunday. Additionally, galaxies interact with each other. Within clusters, galaxies orbit the cluster center while also experiencing close encounters with other cluster members. These interactions can transfer energy and momentum, redistributing velocities and sometimes ejecting galaxies from clusters entirely. On the largest scales, however, these complexities average out. The overall flow, the bulk motion of thousands of galaxies, is smooth and coherent, directed toward mass concentrations. This is what we observe: a cosmic river carrying everything in our neighborhood toward the Great Attractor. Our peculiar velocity of 627 kilometers per second represents our departure from the pure Hubble flow. If expansion were the only factor, our velocity relative to the CMB rest frame would be zero. Instead, we're moving, pulled by the combined gravity of the Virgo cluster, the Great Attractor, the Shapley supercluster, and all the dark matter associated with these structures. This motion will continue for billions of years. We're not in immediate danger of falling into the Great Attractor. The distances are enormous, and cosmic expansion slows our approach. But gradually, over eons, we'll drift closer to Laniakea's core, merging with other galaxies and settling into denser structures. Dark matter is perhaps the greatest mystery in modern astrophysics. We know it exists, the evidence is overwhelming, yet we don't know what it is. And it's everywhere, dominating the universe's mass and shaping cosmic structure on all scales. The story of dark matter begins in the 1930s when astronomer Fritz Zwicky studied the Coma cluster, a massive galaxy cluster about 320 million light-years away. Zwicky measured the velocities of galaxies within the cluster and applied the virial theorem, a physical law relating a system's kinetic energy to its gravitational potential energy, to estimate the cluster's mass. His result was startling. The cluster's mass, calculated from galaxy velocities, was about 400 times larger than the mass estimated from the visible light of its galaxies. Something unseen must be providing the gravitational glue holding the cluster together. Zwicky called it Dunkel materia, dark matter. For decades, Zwicky's finding was largely ignored. The discrepancy seemed too large, possibly reflecting errors in assumptions or measurements, but evidence accumulated. In the 1970s, Vera Rubin and Kent Ford measured rotation curves, how orbital velocities vary with distance from galactic centers for spiral galaxies. They expected velocities to decrease with distance, following Kepler's laws for a mass concentrated at the center. Instead, rotation curves remained flat, far beyond the visible disk. Stars at great distances from galactic centers orbited just as fast as stars near the center. This implied that galaxy mass extended far beyond the visible star's invisible mass, distributed in enormous halos surrounding galaxies. The halos had to be dark, not emitting light, and massive, containing more mass than the visible galaxy. Subsequent observations confirmed dark matter's ubiquity. Gravitational lensing, where massive objects bend light from background sources, revealed dark matter distributions in clusters. X-ray observations showed hot gas in clusters held by gravitational wells far deeper than visible matter could produce. The cosmic microwave background's fluctuation pattern matched predictions only if dark matter comprised about 85% of all matter. Today, the standard cosmological model includes dark matter as a fundamental component. It makes up about 27% of the universe's total energy density. Ordinary matter is only about 5%. Dark energy, driving accelerating expansion, is about 68%. But what is dark matter? We don't know. The leading hypothesis involves WIMPs weakly interacting massive particles. These would be new particles, not part of the standard model of particle physics, interacting only through gravity and the weak nuclear force. Numerous experiments have searched for WIMPs using detectors deep underground to shield from cosmic rays, but none have found definitive evidence. Other candidates include Axion's extremely light particles proposed to solve a problem in quantum chromodynamics, sterile neutrinos, hypothetical heavier cousins of known neutrinos, and primordial black holes formed in the early universe from density fluctuations. Each has theoretical motivations and observational constraints, but none has been confirmed. The possibility also exists that dark matter doesn't consist of particles at all, but reflects modifications to gravity on large scales. Modified Newtonian dynamics, MOND, and similar theories propose that gravity behaves differently at very low accelerations, mimicking dark matter's effects without requiring new particles. While MOND succeeds in explaining galaxy rotation curves, it struggles to match observations of clusters and the cosmic microwave background, where particle dark matter fits better. Whatever its nature, dark matter shapes the Great Attractor. The region's enormous gravitational pull comes primarily from dark matter in visible mass, concentrated in halos around galaxies and pervading the space between them. Visible galaxies and hot gas contribute, but dark matter dominates. Simulations of cosmic structure formation include dark matter as a key ingredient. Starting from initial conditions based on the cosmic microwave background's fluctuations, these simulations evolve the universe forward in time, tracking how matter clumps under gravity's influence. The results match observed large-scale structure remarkably well. The cosmic web of filaments, nodes, and voids emerges naturally. These simulations show that massive structures like the Great Attractor form, where dark matter halos merge and accumulate. Multiple halos combine into cluster-scale halos, which themselves merge into supercluster complexes. The Great Attractor region represents such a convergence, a place where the cosmic web's filaments intersect, creating a dark matter overdensity that dominates local dynamics. Without dark matter, the Great Attractor couldn't exist. Ordinary matter alone, galaxies and hot gas, provides too little mass to create the observed gravitational pull. Dark matter, though invisible, supplies the gravitational backbone. This highlights a cosmic irony. The universe's dominant form of matter is invisible to us. We observe the cosmos through light, yet most of what shapes it cannot be seen. Dark matter reveals itself only through gravity's effects, the motion of galaxies, the bending of light, the hot gas held in place. The Great Attractor is, at its core, a dark matter phenomenon. Let's bring this cosmic picture back to our immediate neighborhood, the local group, our small cluster of galaxies making its way through the universe. The local group spans roughly 10 million light-years across and contains about 80 known galaxies. 3 dominate: the Milky Way, the Andromeda Galaxy M31, and the Triangulum Galaxy M33. The rest are dwarf galaxies, small systems with millions to a few billion stars compared to the hundreds of billions in the major spirals. The Milky Way and Andromeda are the group's gravitational anchors. They orbit each other, or more precisely, orbit their common center of mass, while the dwarf galaxies orbit one or the other, or in some cases, both. Andromeda is the larger of the two, with a mass roughly 1.5 times the Milky Way's. It's about 2.5 million light-years away, close enough that, under dark skies, it's visible to the naked eye as a faint smudge of light. It's the most distant object commonly visible without optical aid. The Milky Way and Andromeda are approaching each other at about 110 kilometers per second. Their mutual gravitational attraction overcomes the universe's expansion at their relatively close separation. They're on a collision course, destined to merge in approximately 4 to 5 billion years. When they collide, the results will be spectacular to any observers who might exist then. Stars themselves won't collide. Space is too vast, and individual stellar encounters are rare. But the galaxy's gas clouds will slam together, triggering massive bursts of star formation. Gravitational interactions will distort both galaxies, flinging stars into enormous tidal tails, stretching millions of light-years. Over hundreds of millions of years, the galaxies will pass through each other, separate, then fall back together again. Eventually, they'll merge into a single elliptical galaxy, sometimes nicknamed Milkomeda or Milkdromeda. The merger remnant will be more massive than either progenitor, its stars orbiting in random orientations rather than a flat disk. Triangulum, the third major galaxy, may be swept up in this merger or may be ejected to the local group's outskirts. Simulations show various outcomes depending on initial conditions. But while the Milky Way and Andromeda dance toward their eventual merger, the entire local group moves through space, pulled by larger structures. The nearest major structure beyond the local group is the Virgo cluster, about 54 million light-years away. The Virgo cluster contains over 1,500 galaxies, including massive elliptical galaxies like M87 famous for the first direct black hole image in 2019. Its total mass is roughly 10-15 solar masses, 1,000 Milky Ways. The local group falls toward the Virgo cluster at approximately 300 kilometers per second. We won't collide directly. Our approach angle and initial velocity mean we're on a long, elliptical orbit around Virgo rather than a collision course. But Virgo's gravity shapes our motion, curving our path through space. Beyond Virgo, the Great Attractor pulls. The local group's velocity toward the Great Attractor region is about 600 kilometers per second after accounting for the Virgo component. This is the dominant contribution to our peculiar velocity. The Great Attractor, not Virgo, primarily sets our cosmic course. And beyond the Great Attractor, the Shapley supercluster adds its pull. Our velocity toward Shapley is harder to isolate since the Great Attractor lies in the same general direction, but studies suggest it contributes 200 to 300 kilometers per second to our motion. The vector sum of all these components, Andromeda's pull, Virgo's pull, the Great Attractor's pull, and Shapley's pull, produces our net peculiar velocity of 627 kilometers per second toward a point in the constellation Centaurus. This velocity is measured relative to the cosmic microwave background, CMB, the radiation left over from the universe's hot early phase, about 380,000 years after the Big Bang. The CMB fills the universe uniformly, providing a natural rest frame. Our motion through this frame creates a dipole pattern. The CMB appears slightly hotter, blue-shifted in the direction we're moving, slightly cooler, red-shifted in the opposite direction. The CMB dipole's measured magnitude corresponds perfectly to a velocity of about 627 kilometers per second towards Centaurus, confirming our peculiar velocity determination from galaxy surveys. These independent measurements agree, validating our understanding of cosmic flows. What does this motion mean for us? In everyday terms, nothing noticeable. We can't feel our motion through space any more than we can feel Earth's motion around the Sunday. Space is uniform. There are no potholes or speed bumps to jolt us. We race through the cosmos at 1.4 million miles per hour, yet perceive only stillness. But astronomically, this motion is significant. It connects us to the universe's large-scale structure, to the cosmic web of filaments and clusters, to the gravitational forces shaping matter across hundreds of millions of light-years. Our velocity is a signature of the Great Attractor's influence, evidence of the invisible dark matter shaping our path. And this journey continues. For billions of years, the local group will flow through space, approaching the Great Attractor region, merging with other groups, eventually settling into Laniakea's core. Long before that, the Milky Way and Andromeda will merge, creating a new galaxy that will inherit our cosmic trajectory. In 1998, two independent teams of astronomers made a shocking discovery. The universe's expansion is accelerating. They had measured the brightness and redshift of Type Ia supernovae stellar explosions that serve as standard candles because they have consistent luminosity. By comparing brightness, which indicates distance, to redshift, which indicates velocity, they could map the expansion rate over cosmic time. They expected to find that expansion was slowing down, as gravity from all the universe's matter pulled back on receding galaxies. Instead, Distant supernovae were fainter than expected, farther away than the standard deceleration model predicted. The expansion wasn't slowing down, it was speeding up. This acceleration requires something pushing space apart, something counteracting gravity. Astronomers call it dark energy, and it comprises about 68% of the universe's total energy density. We don't know what dark energy is. The simplest possibility is the cosmological constant, a constant energy density pervading all space, equivalent to a property of the vacuum itself. Einstein originally introduced a cosmological constant in 1917 to create a static universe, before Hubble discovered expansion, then called it his biggest blunder when expansion was confirmed. Now it's back, in a different form, driving acceleration. Other possibilities include quintessence, a dynamic field whose energy density can vary in space and time, or modifications to general relativity on cosmological scales. No observations yet distinguish between these options. The cosmological constant remains the simplest fit. Dark energy has profound implications for the Great Attractor and cosmic structure. On small scales, galaxies, galaxy groups, even galaxy clusters, dark energy doesn't matter much. Gravitational binding is strong enough to overcome the accelerating expansion. The Milky Way, the Local Group, and the Virgo cluster will remain gravitationally bound forever, or until they merge into a single structure. But on larger scales, dark energy dominates. It prevents the gravitational collapse of superclusters and eventually tears apart structures that aren't gravitationally bound. Laniakea, despite being called a supercluster, is not gravitationally bound. The velocities of galaxies flowing toward its center are insufficient to overcome accelerating expansion for galaxies near the edges. Over billions of years, dark energy will stretch Laniakea apart, isolating its constituent clusters into separate islands receding from each other. The Great Attractor's pull, therefore, is temporary on cosmic timescales. We're flowing toward it now, and this flow will continue for billions of years. But eventually, expansion will accelerate enough that the flow weakens and ceases. In the far future, perhaps 100 billion years from now, the observable universe will look very different. The local group, or its merged descendant, will be isolated. Distant galaxies and clusters will have receded beyond the cosmic horizon. Their light redshifted into invisibility, their gravitational influence cut off by expansion faster than light. Observers in that distant epoch, if any exist, will see only their local cluster of galaxies, surrounded by apparent emptiness. They'll have no direct evidence of the cosmic web, the CMB, or the universe's expansion. Without preserved records from earlier epochs, they might conclude they inhabit a static, isolated island in an otherwise empty cosmos. This big freeze, or heat death scenario, represents one possible ultimate fate of the universe, a cold, dark, dilute expanse, where isolated stellar remnants slowly decay over unimaginable timescales. But that fate lies impossibly far in the future. For now, and for billions of years to come, the Great Attractor still pulls. Dark energy is accelerating expansion, but the effect is gradual. The cosmic flows we observe today will persist for eons, shaping galaxy distributions across Laniakea. The Great Attractor represents our current cosmic trajectory, the direction we're heading in this particular epoch of cosmic history. Future epochs will bring changes, mergers, flows, and eventually dissolution as dark energy's influence grows. But for now, we sail toward the Great Attractor, participants in a gravitational river billions of years in the making. Despite decades of study, the Great Attractor remains one of the most challenging objects to observe directly. The zone of avoidance persists as an obstacle, and the region's complexity, multiple clusters, filaments, and diffuse matter makes interpretation difficult. Yet progress continues. Each generation of telescopes and surveys reveals more about this hidden cosmic structure. The Parkes Radio Telescope in Australia conducted the Parkes HI Zone of Avoidance Survey, one of the most comprehensive radio studies of the region. By mapping 21 cm hydrogen emission, this survey detected over 1,000 galaxies behind the Milky Way's obscuring disk, including many in the Great Attractor direction. The survey revealed the Norma cluster's true extent, a massive, rich cluster comparable to the Coma cluster in the northern sky. It also found numerous smaller groups and isolated galaxies, filling in the previously blank map of this cosmic territory. The 2-mass redshift survey extended the 2-micron all-sky survey by obtaining spectra and hence redshifts and distances for thousands of galaxies detected in the infrared survey. This allowed three-dimensional mapping of the zone of avoidance's structures, revealing the Great Attractor's complex topology. X-ray surveys from satellites like ROSAT, XMM Newton, and Chandra detected hot intracluster gas in several clusters behind the galactic plane. The Norma cluster shines brightly in X-rays, its gas heated to tens of millions of degrees by the cluster's gravitational compression. Other clusters in the Great Attractor region also emit X-rays, mapping the distribution of massive structures. The Cosmic Flows Project, led by R. Brent Tully and colleagues, has measured peculiar velocities for tens of thousands of galaxies using various distance indicators. These measurements enable increasingly precise maps of the cosmic velocity field, revealing the Great Attractor's influence and its relationship to Laniakea. Recent surveys have expanded our understanding further. The Hippus HI Parkes All-Sky Survey mapped neutral hydrogen across the southern sky, detecting thousands of gas-rich galaxies, including many in the zone of avoidance. The WISE Wide-Field Infrared Survey Explorer satellite provided mid-infrared data across the entire sky, penetrating dust more effectively than optical surveys. The discovery of the Vela supercluster in 2017 added another piece to the puzzle. Lying partly in the zone of avoidance at about 800 million light-years distance, the Vela supercluster is comparable in mass to the Shapley supercluster. Its gravitational influence may contribute to our peculiar velocity, adding another layer to the hierarchical flow. Future observatories promise even deeper insights. The Square Kilometre Array, SKA, currently under construction in Australia and South Africa, will be the world's largest radio telescope. Its unprecedented sensitivity will enable detailed 21C mapping across the zone of avoidance, potentially resolving structures too faint for current instruments. The Vera C. Rubin Observatory, beginning operations in Chile, will conduct the Legacy Survey of Space and Time, LSST, a decade-long survey imaging the entire southern sky repeatedly. While the zone of avoidance remains difficult at optical wavelengths, the LSST will map structures near its edges with exquisite precision, improving our understanding of the cosmic web's architecture. The James Webb Space Telescope, JWST, though primarily designed for other purposes, can observe selected targets in the infrared with unprecedented depth. Pointed observations of Great Attractor structures could reveal faint galaxies and details invisible to previous instruments. Even as technology advances, fundamental challenges remain. The Milky Way's dust isn't going anywhere, it will always obstruct our view toward the galactic plane. Multi-wavelength observations help, but can't eliminate the problem entirely. Some galaxies will remain forever hidden, their light absorbed by intervening dust. Indirect methods measuring gravitational effects rather than light offer another approach. Gravitational lensing by the Great Attractor region could distort the shapes and positions of background galaxies, revealing the mass distribution without requiring direct observation. Current surveys have limited sensitivity to such effects at the Great Attractor's distance, but future missions might detect subtle lensing signatures. Despite these challenges, our picture of the Great Attractor has evolved dramatically since its discovery. What began as a mysterious something pulling galaxies has resolved into a complex region. The Norma cluster and surrounding structures, embedded in a massive dark matter overdensity, connected to the Shapley supercluster and the broader Laniakea basin. The Great Attractor isn't a single object, but a convergence, a place where the cosmic web's filaments intersect, where matter accumulated over billions of years, where gravity created a basin of attraction spanning hundreds of millions of light years. It's our cosmic destination, the direction our neighborhood flows, a signpost marking our path through the universe. The Great Attractor exists within a larger context, the cosmic web, the universe's grand architecture of filaments, nodes, and voids. This web emerged from the primordial fluctuations, tiny density variations imprinted during cosmic inflation and amplified by gravity over 13.8 billion years. Where the early universe was slightly denser, gravity attracted more matter, creating overdensities that grew into galaxies and clusters. Where it was slightly underdense, expansion emptied these regions into voids. The cosmic web has a hierarchical structure. Galaxies are the fundamental building blocks, collections of stars, gas, and dark matter, ranging from dwarf systems with millions of stars to giant ellipticals with trillions. Galaxy groups are small collections of galaxies, typically 10 to 50 members held together by mutual gravity. The local group is an example, with its 80 or so known members. Galaxy clusters are larger collections, hundreds to thousands of galaxies embedded in hot gas and dark matter halos. The Virgo cluster, the Norma cluster, and the Coma cluster are examples. Superclusters are vast assemblages of clusters and groups, spanning hundreds of millions of light years. They're the largest gravitationally coherent structures, though not necessarily gravitationally bound. Laniakea is our local supercluster. Filaments are linear structures, chains of galaxies and groups stretching tens to hundreds of millions of light years. They connect nodes, clusters, and superclusters in the cosmic web. Walls or sheets are two-dimensional structures where filaments intersect, creating planar concentrations of galaxies. Voids are the underdense regions, vast expanses with few galaxies, spanning 100 to 400 million light years. They occupy most of the universe's volume. Together, these components form the cosmic web, a foam-like structure where matter concentrates on bubble surfaces and edges, surrounding empty interiors. Observations confirm this structure across the observable universe. Galaxy surveys like the Sloan Digital Sky Survey, SDSS, and 2DF Galaxy Redshift Survey mapped millions of galaxies in 3 dimensions, revealing the web's intricate patterns. Filaments stretch like bridges between clusters, voids yawn as dark expanses with few galaxies. Simulations reproduce this structure remarkably well. Starting from initial conditions based on the cosmic microwave background, computer models evolve the universe forward under gravity's influence. The resulting structures, filaments, nodes, voids match observations closely, validating our understanding of structure formation. The Great Attractor is a node in this web, a place where multiple filaments converge, creating a mass concentration. Galaxies flow along the filaments toward the node, like water flowing through tributaries toward a river junction. Laniakea is the drainage basin containing these filaments and flows. Its boundaries, watersheds in velocity space, separate it from neighboring basins flowing toward different attractors. Beyond Laniakea lie other superclusters. The Perseus-Pisces supercluster, a massive structure in the northern sky. The Coma supercluster, centered on the rich Coma cluster. The Hercules supercluster, containing several prominent clusters, and many others. Each is a separate basin with its own flow pattern. The cosmic web extends across the observable universe. The farthest structures we observe quasars and galaxies at redshifts of 7 to 10, when the universe was less than 1 billion years old, already show filamentary distributions, though less developed than today's mature web. This ubiquity reflects the cosmic web's fundamental origin, gravity amplifying primordial fluctuations. Given the initial conditions set during inflation and the laws of physics, the web was inevitable. Any universe with matter and gravity would develop similar large-scale structure. The Great Attractor, then, is not unique. Similar structures exist throughout the cosmos, massive convergences at filament intersections, pulling galaxies across vast distances. We call ours the Great Attractor, simply because it's nearby and influences us. Observers in distant galaxies, billions of light-years away, would have their own great attractors, local nodes, shaping their cosmic motion. Understanding this context provides perspective. The Great Attractor seems vast and powerful, and it is, from our vantage point. But cosmically, it's a typical feature of the universe's large-scale structure, one node among countless others, a representative example of how gravity organizes matter across cosmic time. Yet it's also special to us. It's our node, the gravitational basin toward which we flow, the destination of our cosmic journey. Studying it teaches us about structure formation, dark matter, and our place in the grand cosmic architecture. One of the Great Attractor's most fascinating aspects is how we discovered it without seeing it. The entire detection relied on measuring motion, watching how galaxies move to infer what pulls them. This indirect approach is common in astronomy. We rarely observe cosmic phenomena directly. Instead, we detect their effects and work backward to understand their causes. Dark matter is invisible, but we measure its gravitational influence. Black holes emit no light, but we observe matter spiraling toward them. The Great Attractor hides behind our galaxy, but we track the galaxies it pulls. The key measurement is peculiar velocity, a galaxy's motion relative to the Hubble flow. If a galaxy simply rode the expansion, its velocity would be v equals h0 times d, where h0 is the Hubble constant and d is distance. Any deviation from this, moving faster or slower than expansion predicts, is peculiar velocity. Measuring peculiar velocity requires two independent quantities: the galaxy's distance to calculate expected Hubble velocity and its observed velocity from redshift. The difference between expected and observed velocities is the peculiar velocity. Distance measurement is the challenge. Redshift is easy. You take a spectrum, measure spectral line positions, and calculate how much they've shifted. But redshift combines Hubble flow and peculiar velocity. You can't separate them without an independent distance estimate. Astronomers have developed numerous distance ladders, chains of methods that calibrate each other. Nearby distances use parallax, the apparent shift of stars as Earth orbits the Sun. More distant measurements use Cepheid variables, type Ia supernovae, the Tully-Fisher relation, the fundamental plane, and other techniques. Each method has systematic uncertainties. Cepheids require careful calibration of the period-luminosity relation. Supernovae vary slightly in brightness and require corrections. The Tully-Fisher and fundamental plane relations have scatter. Not every galaxy follows them exactly. These uncertainties propagate into peculiar velocity estimates. Despite these challenges, consistent patterns emerge. When thousands of galaxy peculiar velocities are mapped, coherent flows appear, streams of galaxies moving toward common destinations. The Great Attractor was discovered this way, not by seeing it, but by measuring the river of galaxies flowing toward it. Modern techniques continue to refine these measurements. The Cosmic Flows series of surveys has compiled peculiar velocities for tens of thousands of galaxies, enabling increasingly detailed maps of cosmic flow. Statistical methods like Wiener filtering extract smooth velocity fields from noisy data, revealing the underlying attractor distribution. Gravitational lensing offers another window on invisible mass. When light from distant galaxies passes through or near a massive structure, gravity bends its path. This bending distorts galaxy images, stretching them tangentially around mass concentrations and magnifies their brightness. By measuring these distortions across many background galaxies, astronomers can reconstruct the foreground mass distribution, including both visible and dark matter. This technique has mapped dark matter in clusters and, increasingly, in larger structures like filaments and superclusters. In principle, gravitational lensing could map the Great Attractor's mass distribution even though we can't see it directly. In practice, the Great Attractor is relatively nearby by cosmological standards, making lensing effects subtle and difficult to detect. Future surveys with higher precision may accomplish this measurement. Another approach uses the cosmic microwave background, CMB. As CMB photons travel toward us, they pass through cosmic structures. Hot gas in clusters scatters CMB photons, creating a characteristic signature called the Sunyaev-Zeldovich effect. This effect is independent of redshift, allowing detection of clusters even in the zone of avoidance. Surveys like the Planck satellite's all-sky CMB observations have detected the Sunyaev-Zeldovich effect from numerous clusters, including some in the Great Attractor direction. These detections confirm the presence of massive structures and provide mass estimates independent of optical observations. The CMB also reveals our motion through the kinematic dipole. Because we're moving towards Centaurus at 627 kilometers per second, we see slightly blue-shifted, hotter CMB radiation in that direction and red-shifted, cooler radiation in the opposite direction. This dipole's magnitude and direction match the peculiar velocity inferred from galaxy surveys, providing independent confirmation of the Great Attractor's influence. Together, these techniques, peculiar velocity measurements, gravitational lensing, the Sunyaev-Zeldovich effect, and the CMB dipole paint a consistent picture. A massive concentration exists in the Centaurus Norma Hydra region, pulling thousands of galaxies toward it at hundreds of kilometers per second. We call it the Great Attractor, even though we can barely see it. This indirect detection exemplifies modern astronomy's power. We need not see an object to know it exists. Measuring its effects suffices. The Great Attractor, hidden behind our galaxy, revealed itself through the galaxies it pulls, a gravitational ghost detected by its shadow. The Great Attractor's discovery unfolded over decades, involving multiple research teams, advancing technology, and evolving understanding. Tracing this history illuminates how scientific knowledge develops through observation, theory, debate, and synthesis. The story begins with cosmology's foundations in the early 20th century. Einstein's general relativity, 1915, provided the theoretical framework for understanding gravity on cosmic scales. Hubble's discovery of the expanding universe, 1929, established the Hubble flow as the baseline motion of galaxies. But Hubble's law describes the average behavior. Individual galaxies deviate from it. In the 1950s, astronomers began measuring these deviations' peculiar velocities for nearby galaxies. Results suggested small, seemingly random motions, a few hundred kilometers per second at most. The local group's motion relative to the Virgo cluster was recognized early. The Virgo cluster, being massive and nearby, should gravitationally attract us. Observations confirmed we're moving toward Virgo at a few hundred kilometers per second, our infall into the nearest large cluster. But the full picture didn't emerge until the 1970s and 1980s. Two developments made this possible: improved distance indicators and larger galaxy surveys. The Tully-Fisher relation, 1977, provided a practical tool for estimating spiral galaxy distances. By measuring a galaxy's rotation speed from radio or optical spectroscopy and its apparent brightness from photometry, astronomers could estimate distance. This enabled peculiar velocity measurements for hundreds of galaxies. The Faber-Jackson relation, 1976, and its refinements provided similar tools for elliptical galaxies. The fundamental plane combined elliptical galaxies' velocity dispersion, surface brightness, and size into a distance indicator with reasonable accuracy. With these tools, astronomers began systematic surveys. The seven samurai Faber, Burstein, Davies, Dressler, Lynden-Bell, Turlevich, and Wegener measured distances and velocities for 400 elliptical galaxies across a significant volume of space. Their 1986 paper, published in the Astrophysical Journal, announced the discovery: a large-scale coherent motion toward a point in the southern sky far larger than Virgo's influence alone could explain. They estimated the attractor's mass and location, coining the term Great Attractor. The discovery was controversial. Some astronomers questioned the methodology. Were the distance measurements accurate enough? Could systematic errors mimic coherent flows? Alternative explanations were proposed, including statistical flukes or calibration issues, but independent studies confirmed the result. Other teams, using different distance indicators and galaxy samples, found similar coherent motions toward the Centaurus Hydra region. The peculiar velocity field wasn't a fluke. Something massive really existed there. The next challenge was identifying what the Great Attractor was. Direct observations were thwarted by the zone of avoidance. The attractor lay behind the Milky Way's disk. Optical searches found some galaxies in the region but couldn't see the full extent of the structure. Infrared and radio surveys gradually filled in the picture. The Parkes radio telescope detected numerous galaxies via their hydrogen emission. Infrared surveys like 2MASS penetrated the dust, revealing galaxy overdensities consistent with a massive cluster or supercluster. The Norma cluster, Abell 3627, emerged as a central component, a massive, rich cluster hiding almost exactly where the Great Attractor's gravitational center was predicted. X-ray observations confirmed its enormity. Hot gas pervading the cluster, held by a gravitational well comparable to the largest known clusters. But the Norma cluster alone couldn't explain everything. Even accounting for all visible mass in the Great Attractor region, the gravitational pull seemed insufficient. Dark matter filled the gap in visible mass, dominating the region's gravitational potential. Meanwhile, velocity surveys extended to larger scales, revealing that the Great Attractor itself was moving, falling toward an even more massive structure behind it. This led to recognition of the Shapley supercluster's importance. The Shapley concentration, documented since the 1930s but not fully appreciated, emerged as the dominant mass concentration in the nearby universe. Studies in the 1990s and 2000s quantified its influence, showing it pulls the Great Attractor, and us along with it, at several hundred kilometers per second. The 2014 Laniakea paper synthesized these findings. Tully, Courtois, Hoffman, and Pomered mapped the cosmic velocity field across a vast volume, identifying Laniakea as a coherent basin of attraction. The Great Attractor, Shapley, Virgo, and thousands of other structures belong to a single supercluster, our cosmic home. This evolution from the Great Attractor's discovery to Laniakea's identification took nearly 3 decades. It involved hundreds of astronomers, multiple telescope facilities, and advancing theoretical understanding. The story continues today as new surveys and instruments refine our picture of cosmic flows. The Great Attractor offers lessons beyond astronomy. It illuminates our place in the cosmos, challenging assumptions about centrality, permanence, and significance. For most of history, humans believed Earth was the cosmic center, the still point around which everything revolved. The Copernican revolution displaced us, placing the Sun at the center of the solar system. Later revolutions pushed farther. The Sun orbits the Milky Way's periphery. The Milky Way is one galaxy among billions. The universe has no center. The Great Attractor extends this narrative. We're not only moving through space, but being pulled by invisible forces toward destinations beyond our view. The cosmic web structure shapes our trajectory. Dark matter guides our path. We're not masters of our motion, but passengers on a gravitational river flowing through the cosmos. This might seem humbling, even disorienting, but it's also connecting. We're not separate from the universe, but embedded within it, participants in its grand architecture. The same forces that shaped the cosmic web shaped us. The same atoms forged in stars compose our bodies. Our motion toward the Great Attractor is continuous with the universe's evolution since the Big Bang. The Great Attractor also illustrates science's power to reveal the invisible. We discovered this massive structure without seeing it by measuring its effects on visible galaxies. We mapped dark matter, without detecting its particles, by observing its gravitational influence. We inferred the cosmic web's structure by analyzing how matter flows. This detective work, building pictures of reality from indirect evidence, defines much of modern science. We understand atoms through their spectra, black holes through their surroundings, dark energy through its acceleration. The Great Attractor exemplifies this indirect approach, demonstrating that the invisible can become known through its effects. Finally, the Great Attractor reminds us that the universe is dynamic. Nothing stands still. Everything moves, evolves, transforms. Stars form and die. Galaxies collide and merge. Superclusters stretch and dissolve. The cosmos we observe today is a snapshot in a vast movie, a single frame in a story spanning 13.8 billion years and continuing toward an uncertain future. Our motion toward the Great Attractor is part of this dynamism. We're not static observers but participants in cosmic evolution, flowing toward our gravitational destiny. Billions of years from now, the Milky Way will merge with Andromeda, the local group will settle into Laniakia's core, and dark energy will isolate us from the broader cosmos. But these transformations lie far in the future. For now, the Great Attractor beckons, and we answer. Despite decades of study, many questions about the Great Attractor remain unanswered. These mysteries drive ongoing research and promise future discoveries. What is the Great Attractor's exact mass? Estimates range from 10, 16 to several times 10, 16 solar masses. But uncertainties persist. Different techniques, velocity field analysis, X-ray gas observations, gravitational lensing give somewhat different answers. Reconciling these estimates requires better data and more sophisticated modeling. What is the Great Attractor's precise structure? Is it primarily the Norma cluster, or a more extended overdensity? How do surrounding structures, the Centaurus cluster, the Pavo-Indus supercluster, the Shapley supercluster, contribute to the total gravitational pull? Mapping this complex region in detail remains challenging due to the zone of avoidance. Is there something beyond Shapley pulling it? Some studies suggest residual velocity even after accounting for Shapley's influence. The Vela supercluster and other distant structures may contribute. Determining the full hierarchy of gravitational influences requires even larger surveys with even greater precision. What is dark matter? The Great Attractor's gravitational pull comes primarily from dark matter, yet we don't know what dark matter is. Identifying the dark matter particle or discovering that dark matter isn't particulate would revolutionize our understanding of the universe's dominant form of matter. How will dark energy affect the Great Attractor's future? As accelerating expansion stretches space, will the cosmic flows we observe today eventually cease? When will Laniakea dissolve into isolated clusters? Predicting the cosmic future requires understanding dark energy better than we currently do. Are there undiscovered structures in the zone of avoidance? Despite progress, significant portions of the sky remain poorly mapped. Major clusters or superclusters might lurk behind the Milky Way's disk, their gravitational influence felt but their nature unknown. Future surveys may reveal these hidden giants. These questions motivate ongoing research programs. Large galaxy surveys continue to measure peculiar velocities with increasing precision. New telescopes, the Square Kilometre Array, the Vera Rubin Observatory, space-based infrared missions promise deeper views of the hidden cosmos. Theoretical models incorporate dark energy and dark matter to predict the universe's future evolution. The Great Attractor, despite its name, is not the end of the story. It's a chapter, a significant one in our understanding of cosmic structure. Future chapters will answer current questions and, inevitably, raise new ones. That's the nature of science. Each discovery reveals deeper mysteries. Each answer spawns new questions, and the exploration continues without end. If you could travel to a planet in the Great Attractor region, perhaps a world orbiting a star in the Norma cluster, what would the sky look like? You'd be embedded within a rich galaxy cluster, surrounded by hundreds of nearby galaxies. The sky would blaze with light, giant elliptical galaxies glowing golden with ancient stars, spiral galaxies splashed across the darkness, dwarf galaxies sprinkling the field like cosmic confetti. The Milky Way would appear as a distant spiral, approximately 220 million light-years away, visible through a modest telescope, perhaps, but unremarkable among the thousands of galaxies in your local environment. It would be part of a filament stretching toward your cluster, one stream among many feeding the local gravitational basin. Looking outward from the Norma cluster, you'd see the cosmic web's architecture spreading in all directions. Filaments of galaxies would stretch toward other clusters, the Centaurus cluster in one direction, the Pavo-Indus structures in another, the vast Shapley supercluster dominating a swath of sky. Your peculiar velocity would differ from ours. Instead of falling toward the Great Attractor, you'd be near its center, moving slowly relative to the local average, perhaps orbiting within the cluster's gravitational well. The Shapley supercluster would pull you outward, but the cluster's gravity would hold you in place. The cosmic microwave background would show a different dipole pattern, fainter, perhaps, if your motion through the CMB rest frame were slower than ours. The universe's large-scale structure would be the same, but your perspective on it would shift. This thought experiment illustrates an important point. The Great Attractor isn't special except to us. It's significant because we're falling toward it, because it shapes our cosmic trajectory. Observers elsewhere in the universe have their own great attractors, local mass concentrations, pulling them through space. The universe has no center, no preferred location. Every observer sees themselves as stationary and others as moving. Every galaxy is at the center of its own observable universe, surrounded by the same cosmic web patterns receding in every direction. The Great Attractor is our attractor, the gravitational basin we inhabit, the destination we're approaching. Other observers have other attractors, equally significant from their perspectives. The cosmos is democratically structured. No location is privileged, yet every location is embedded in the same grand architecture. We've journeyed from Earth's orbit around the Sun to the Milky Way's motion through the galaxy, to the galaxy's flow through the local group, the local group's fall toward Virgo, and Virgo's stream toward the Great Attractor. We've zoomed out to see Laniakea, our true cosmic home, and the web of superclusters beyond. At every scale, motion. At every scale, structure. And at every scale, gravity shaping, pulling, organizing the universe into the magnificent architecture we observe. The Great Attractor is a reminder that we're not separate from the cosmos but embedded within it, participants in flows and structures spanning hundreds of millions of light-years. Our galaxy is a tiny piece of a vast gravitational system moving through space at over 1 million miles per hour, pulled by mass concentrations we can barely see, yet we've discovered these hidden structures. Through careful observations of galaxy motions, through infrared and radio surveys piercing the zone of avoidance, through mapping the cosmic web's flows, we've revealed the Great Attractor's nature and our place within Laniakea. This knowledge transforms how we see ourselves. Our cosmic address is longer than we thought. Earth, Solar System, Orion Arm, Milky Way, Galaxy, Local Group, Local Sheet, Virgo Supercluster Region, Laniakea Supercluster, flowing toward the Great Attractor core, influenced by the Shapley Supercluster within the observable universe. Each level represents a structure shaped by gravity and cosmic evolution. Each connects us to the universe's history, from the Big Bang's initial fluctuations to today's cosmic web. And the journey continues. We're still flowing toward the Great Attractor, still racing through space at 1.3 million miles per hour. This motion will persist for billions of years, gradually bringing us closer to Laniakea's core, where we'll eventually merge with other galaxies and settle into a denser structure. Far in the future, dark energy will isolate us, ending the flow. But for now, the Great Attractor pulls, the Shapley Supercluster beckons, and we sail through the cosmic ocean, carried by gravitational currents older than stars. As you drift to sleep, imagine this motion. Imagine Earth spinning on its axis, completing a rotation every 24 hours. Imagine the Sun circling the Milky Way's center, 250 million years per orbit. Imagine the Milky Way flowing through space, pulled by invisible forces toward a destiny hundreds of millions of light years away. Imagine thousands of galaxies streaming together, caught in the Great Attractor's embrace. Imagine the cosmic web, vast and intricate, sculpted by dark matter and shaped by billions of years of gravitational evolution. Imagine Laniakea, our supercluster home, a basin of attraction spanning 500 million light years. We're not stationary. We've never been stationary. We move through space, through time, through the universe's grand architecture. And that motion connects us to everything, to the dark matter halos guiding our path, to the galaxies sharing our journey, to the structure formation process that began 13.8 billion years ago and continues today. The Great Attractor is more than a gravitational anomaly. It's a signpost marking our path through the cosmos, a node in the web that is our home, a testament to the invisible forces shaping the universe. Rest well, knowing you're part of this cosmic flow. Tomorrow, you'll wake on a planet orbiting a star, in a galaxy racing through space, pulled by an invisible ocean of dark matter toward a destination hundreds of millions of light years away. The Great Attractor calls, and we answer as we have for billions of years, as we will for billions more. Not by choice, but by gravity's inexorable pull, the force that binds the universe and writes its story in the motions of galaxies across the cosmic web. Sweet dreams of gravitational flows, of dark matter concentrations, of galaxies streaming through space like rivers to an ocean. You are a passenger on a cosmic voyage billions of years in the making, moving through a universe far more dynamic and interconnected than the ancients ever imagined. And in that motion, in that flow toward the Great Attractor, we find our place in the cosmos, not stationary, not special, but wonderfully, beautifully connected to everything, participating in the greatest journey of all, the universe exploring itself. Between galaxies lies the intergalactic medium, a vast, nearly empty expanse where matter thins to almost nothing. If space within galaxies seems empty, the space between them is emptier still, perhaps 1 atom per cubic meter, compared to billions of atoms per cubic centimeter in Earth's atmosphere. This intergalactic void is not absolute nothingness. Tenuous gas, mostly hydrogen and helium, remnants of the Big Bang, pervades the space between galaxies. X-ray observations reveal this gas in galaxy clusters, heated to millions of degrees by gravitational compression. But in the voids between clusters, in the vast emptiness separating filaments of the cosmic web, the gas is cold and sparse, nearly invisible. Through this emptiness, light travels. Photons from distant galaxies cross hundreds of millions of light-years, passing through the intergalactic medium largely unimpeded. Some are absorbed by intervening gas, creating absorption lines in galaxy spectra. Some are gravitationally lensed by intervening mass. But most travel unhindered, carrying information about their sources across cosmic distances. The Great Attractor's light, what little reaches us through the zone of avoidance, has traveled 220 million light-years. When these photons left their source galaxies, dinosaurs still walked the Earth. They've journeyed through the cosmic void, while life on our planet evolved from reptilian giants to mammals to primates to humans who now detect and study them. This light travel time creates a peculiar effect. We see the universe as it was, not as it is. The Great Attractor we observe is 220 million years out of date. The Shapley supercluster, 650 million light-years distant, appears as it was before complex life existed on Earth. We cannot know what these structures look like now in any meaningful sense. The information hasn't reached us yet. This temporal dislocation extends throughout astronomy. The cosmic microwave background shows the universe at 380,000 years old, a baby cosmos of hot plasma, before stars or galaxies existed. The most distant galaxies reveal conditions when the universe was less than 1 billion years old. We look across space and thereby look back in time, reconstructing cosmic history from light of different ages. The Great Attractor's gravitational influence, however, travels at the speed of light, just as electromagnetic radiation does. The pull we feel today reflects the mass distribution 220 million years ago. If something catastrophic happened to the Great Attractor region right now, if some cosmic event dispersed its mass, we wouldn't notice for 220 million years. We're responding to the past, guided by ancient gravity toward a destination that may have changed. Of course, such catastrophic changes don't happen on these timescales. The cosmic web evolves slowly. 220 million years is insufficient for major structural changes. The Great Attractor that pulls us today is essentially the same as the Great Attractor whose light now reaches us. The temporal mismatch is real, but cosmologically insignificant. Still, this subtlety reminds us that our cosmic picture is a reconstruction, a model built from ancient light and inferred physics. We don't directly perceive the universe, we interpret signals that have crossed vast distances over vast times. Our understanding is profound yet indirect, a triumph of inference and imagination. The silence of deep space amplifies this. No sound travels through the intergalactic vacuum. There's no medium to carry pressure waves. The cosmic drama unfolds in absolute silence. Galaxies collide without a crash. Stars explode without a boom. The Great Attractor pulls without a whisper. Only light speaks, and we've learned to read its language. There's a profound poetry in our existence. We are matter organized to contemplate matter, energy structured to study energy, the universe become conscious of itself. The atoms in your body were forged in ancient stars, nuclear fusion in stellar cores, explosive nucleosynthesis in supernovae. These atoms drifted through interstellar space for billions of years before gravity gathered them into a new star, our Sun, and a rocky planet, our Earth. Life emerged, evolved, and eventually produced beings who look up at the sky and wonder. Now, through telescopes and mathematics, through satellites and computer simulations, we've discovered the Great Attractor, a gravitational basin pulling us through the cosmos. We've mapped flows across hundreds of millions of light years, traced the invisible dark matter shaping them, and identified our supercluster home. This is remarkable. The universe made beings capable of discovering the universe, of measuring its expansion, mapping its structure, predicting its future. We are not mere passengers on this cosmic voyage, but aware passengers, understanding at least partially where we're going and why. The Great Attractor doesn't know it's attracting us. It's just mass, dark matter, galaxies, and gas-generating gravity as mass does. We are the ones who named it, studied it, puzzled over it. We brought consciousness to a phenomenon that would otherwise unfold in ignorance. In a way, the Great Attractor exists because we discovered it. Before the Seven Samurai published their paper, galaxies still flowed toward the same mass concentration, but the Great Attractor didn't exist as a concept. Our discovery created it, not physically but cognitively, adding a new idea to the universe's self-knowledge. This is what science does. It extends the universe's awareness of itself. Through us, the cosmos learns its own structure. Through our instruments and theories, it measures its own expansion, catalogues its own galaxies, calculates its own fate. We are the universe's means of self-reflection. As you drift to sleep, consider this. You are part of that self-reflection. Your curiosity about the Great Attractor, you're listening to this story, you're wondering about these cosmic flows. Is the universe wondering about itself? Your consciousness, however brief and fragile, participates in the greatest project of all: existence, understanding, existence. The Great Attractor will continue pulling galaxies long after human civilization ends. The cosmic web will evolve over billions of years, its structures changing as dark energy accelerates expansion. Eventually, all flows will cease, all structures will dissolve, and the universe will approach its final state, whatever that may be. But for now, in this cosmic moment, the universe includes beings who know about the Great Attractor. That knowledge is new. It didn't exist a few decades ago. It's part of the universe's evolution, not just physical, but informational, a new pattern in the cosmic data. You carry that pattern in your mind. Tonight, as you sleep, the Great Attractor pulls you through space at 1.4 million miles per hour. But you know it's happening. You understand why. You've traced the cosmic flows, mapped the dark matter, and placed yourself within Laniakere's embrace. That understanding is precious and rare. Most of the universe is unaware. Most matter doesn't know it's matter, but you do. You are the universe, awake to itself, flowing toward the Great Attractor and knowing it. Rest well, dream of cosmic journeys, and remember, in all the billions of light years, in all the hundreds of billions of galaxies, you are part of something extraordinary, the universe's ongoing discovery of itself, written in the motion of galaxies and the awareness of beings who watch them. The Great Attractor calls, we answer, and in our answering, the universe learns.